We will now present to you our thesis entitled Monitoring System of Temperature, Humidity, and Soil Moisture for Vertical Gardening in Urban Environment Setup. My name is Jon M. Kagalingan with my thesis partner, Bernard Piolo and Tolentino, and thesis advisor, Engineer Jessie J.R. Balbin. The objectives of the study includes first is to develop an effective gardening system for an indoor vertical garden in an urban setting, to monitor the growth of the plants by temperature, humidity, and soil moisture using HTML web page, and lastly, to compare the outcome in growth of plants for indoor and outdoor vertical garden. The study has its given scope and limitations, starting with the creation of the prototype that includes programming of ESP32 module, sensor setup, and automated irrigation and humidifier. For the HTML web page, offline mode, Wi-Fi based, receives data from ESP32. And lastly, controlled LED light system that control brightness, LED color, and timer, and has 4 lamps, 2 lights each. The indoor vertical garden setup spans to 60 by 100 centimeters and consisting 16 plants in which there are 2 herbs and 2 peppers. This study is also limited to 16 capacitive soil moisture sensor, DHT11, and 16 water pumps.
Now we go to the conceptual framework. First is the input, which is the data from the sensors, the process, which is the development of the system, and the outputs are the outcomes of plant growth, the automated water irrigation humidifier, and the control of the lighting system. For the complete system flowchart, it has 3 distinct processes for the automated irrigation, humidifier, and the controlled LED lights. Both the irrigation system and the humidifier depend on the given data by the sensor. Each will activate automatically when their corresponding parameter detects low value. So for the LED light system, we have a timer button, a brightness knob, and an LED color selection from blue to red. The indoor vertical garden setup is consisted of 16 plants, the LED lights, prototype, water pump, and reservoir, water dripper, as well as the sensors. The outdoor vertical garden setup is consisted of the same 16 plants. For comparison, prototype is consisted of the following components with the microcontroller ESP32. The controlled LED light shows a controller that has a timer, a color change, and can adjust the brightness of the lights. There are 4 lamps which has 2 lights on each of them. These are the specific connections for the components within the prototype indicated in the circuit diagram. A schematic diagram is provided for the controlled LED light system. For the calibration and test, the sensors were compared against commercially available products. Root mean square error formula was used to evaluate the accuracy for the sensor and the commercial products. For data analysis, the indoor and outdoor vertical gardens were compared in terms of inputs and readings. The table indicates the differences. A statistical analysis is provided for temperature and light, specifically a t-test paired to sample. An ANOVA 2-factor replication will be used for the difference in plant height and average length of leaves. Now let's go to the prototype demonstration.
After turning on the switch and connecting all the DB25 plugs, the prototype can now be activated. To access the HTML web page, insert within the URL section the IP address 192.168.1.100. The web page contains live data for the prototype sensor such as humidity, temperature, and all 16 plants, soil moisture level, updating every 5 seconds. The prototype's 16-channel analog multiplexer lights up, indicating that the soil moisture sensors detect a low value, which activates the corresponding water pump. Keeping in mind that the prototype checks the pots one by one at a time. For example, this plant has a high value of soil moisture level, so in order to activate the water pump, the pot's soil moisture sensor was removed to lower the soil moisture value. In real time, checking the values for the soil moisture is monitored using the HTML web page. The value lowered down when the soil moisture sensor was removed, thus activating the corresponding water pump. The DHT11 sensor detects high value of humidity, thus it stays deactivated. but the humidifier can be manually activated by pushing the button. To turn on the controller, push the red button. The LED lights have output colors in blue and red. Pushing the white switch up will turn off the blue lights. Then turning off the red switch will turn off the red lights. The yellow button is used for the timer. Clicking the yellow button once will set it to 3 hours. 2 clicks for 9 hours, and 3 clicks for a full 12 hours. Using a PWM module, the output of the lights can be changed or controlled. Turning the knob can lower the output or make it brighter.
For the results in the discussion, the t-test for comparison of temperature and applied light, both did not reject the null hypothesis, meaning that the comparisons have no significant difference. P2 tail values are 0.424991 and 0.343436, which is higher than 0.05. For the plant growth of indoor and outdoor basil plants, the table indicates the initial and outcome height and average length of leaves. Table 4 indicates the growth difference of each plant. This is for the indoor and outdoor parsley. This is for the indoor and outdoor bell pepper plants, and the indoor-outdoor chili pepper plants. For the ANOVA test, it indicates that the growth difference for height and average length of leaves accepts the null hypothesis for the first and third hypothesis, which is the sample and interactions, in which it indicates that the setup showed no statistical difference and no significant interactions for the height, average length of leaves, and the vertical garden setup. The second hypothesis, which is the columns, was rejected, meaning that the effects of the setup had significant differences that are applied on each group of plants.
For conclusion, the prototype device can successfully automate irrigation and humidifier, control LED lights, provide monitoring via HTML web page. We also have highest growth difference for height for indoor plants, highest growth difference of average length of leaves for indoor plant and outdoor plants. Also includes highest average growth difference of height for indoor plants, highest average growth difference of average length of leaves for indoor plants and outdoor plants. ANOVA two-way replication for H1 accept null hypothesis, hypothesis 2 reject null hypothesis, and hypothesis 3 accept null hypothesis. For the recommendations, first, larger mesh wire for more quantity of plants. Next, research on other plants and add intervention to taste for plants. Use microcontroller that has more pins. And lastly, better installation of water pumps. Acknowledgement, we would like to thank Engineer Jessie J. R. Balbin of Mapua University, guided us through the study, provided us a path to reach our goals, and shared critical ideas to improve and formulate a practical project, providing with his absolute effort to help us through. He extends his patience and creativity. We would also like to thank our friends and family who supported us through the whole process and were motivating. Furthermore, lastly, we would like to thank God for keeping our faith intact through our university.